I'm going to start with very easy problems, and I'm going to then make them a little bit harder, but it's going to be one of the easiest lectures in this course anyway. So here's my first problem. Suppose that we throw 2 dice. So we toss 2 dice, and these are 2 fair dice. So they have values from 1 to 6 on their sides, and every side is equally probable as every other side. Okay. What is the expected value of the sum? Okay. Now, this is kind of a trivial problem, but the reason I want to start with this is because it really shows you the power of the linearity of expectation in solving problems like this. So here's the thing. Suppose that I define a random variable. So first of all, what is my sample space? I basically have all the possible pairs of x and y such that x and y are between 1 and 6. And every point in my sample space has the same probability, 136. Right? So if I define a random variable, so suppose I define the random variable x, the sum of the value on the 2 dice. Okay. So I want to find the expected value of x. And we said this is just the sum of every possible value. So for every possible value, well, what is the smallest value I can have? The smallest value is 2. Right. And what is the largest value I can have? It's 12. So the sum of x from 2 to 12 of x itself times the probability that the sum is equal to x. Now, this is not impossible to compute, right? It's going to be kind of a headache, but not impossible. You can just go over all 36 of the cases. You can find the probability that x is equal to 2, 3, 4, all the way to 12. And then you can just do this sum, right? But of course, I don't like to do it like that. I want a simpler solution. So I'm just going to say, suppose xi is the number on the ice die. So I'm going to just have x1 and x2. And then my sum is, of course, the sum. So x is equal to x1 plus x2. So I can now say that the expected value of x is just the expected value of x1 plus the expected value of x2. But finding the expected value of x1 is super easy. It's just what is the average value in the first die? What is the average value? My numbers are from 1 to 6. The average value is 3.5, right? So, and these two are also independent of each other. So this one is also 3.5. But very importantly, I don't need independence when I'm using linearity of expectation. So when I proved that I have linearity of expectation, I was not assuming anything about my random variables. I was just using the definition of expectation. So even if my variables are not independent of each other, suppose that somehow I have tied the 2 dice together so that they always show the same number, right? So my 2 dice are not independent of each other, but each one of them is fair on its own. Then still I would have the same thing. Okay, so this is just 3.5 plus 3.5, which is hopefully 7. Okay, so pretty simple. Let's move on. Let's make it a little bit more complicated. So this is my second problem. This one is actually also going to be pretty simple. So suppose that we have a biased coin. And every time that we flip this coin, it comes heads with probability P. So with heads probability P, Now imagine that I flip this coin n times. What is the expected number of heads? Okay. If we flip the coin n times, and let's say x is the random variable, which is the number of heads, the question is, what is the expected value of x? Okay. Intuitively, you know it should be n times p, right? Because I'm flipping it n times. Every time it's going to be heads with probability p, so I would expect that on average I get n times p heads, right? But how would I write this? Again, I can go back to a formula like this, which is the definition, and just say, well, the number of heads is either going to be 0 or 1 or 2 all the way to n. So if I want to do that, just to show you how painful it is, I can do it. I can say the expected value of x is going to be the sum of, well, what is the value that x can take from 0 to n, right? I times the probability that x is equal to I. Okay, and again, my x was my number of heads. So what is the probability that my number of heads is exactly I? So this goes back to our combinatorics lectures, right? So I have n positions. In each of these positions, I have to write either h or t, right? And I want to have exactly I of them to have h and n minus I of them to have t. Okay. So the number of ways of doing that, the probability of x equal to I is what? Well, I have to choose I of these n places to put h's in them. So it's just n choose I, right? But then to get that particular combination, all of these I places, when I flip the coin, I have to get lucky and I have to get heads. So the probability of that is p to the power of I, right? And in every other place, when I flip the coin, I have to get tails. So that's 1 minus p to the power of n minus. Okay. So if I now plug this in back into my definition of expectation, I get a monstrosity like this. The expected value of x is the sum of I from 0 to n of I times n choose I times p to the power of I times 1 minus p to the power of n minus I. Okay, this is correct, but it's ugly. I don't like it. And it takes a long time to compute if I want to compute it algorithmically. So of course, instead of this, I want to somehow use linearity of expectation. I want to write my x as a sum of a bunch of other random variables, such that it's easy for me to calculate the expected value of those other random variables. And then I want to use linearity of expectation. Okay, so I'm going to do the simplest thing. And the simplest thing whenever you're using linearity of expectation is to use indicator random variables. So variables that are either 0 or 1. I'm going to say I define a variable xi, which is going to be 1 if the i's flip of the coin is heads. And it's going to be 0 if the i's flip is tails. Okay. Again, I have that my x is the sum of I from 1 to n of the xi's, right? So the expected value of x is going to be the sum of the expected value of the xi's, and I from 1 to n. What is the expected value of xi? Again, whenever I have an indicator random variable, my expected value is just the probability that it's 1. That's by definition. So what is the probability that xi is 1? So this is the sum of I from 1 to n of the probability that xi is 1. So xi is 1 if the i's flip is heads. But we said that our coin gives us heads with probability p. So the probability that xi is 1 is just p. So this is just the sum of p for I from 1 to n, which is just, I'm summing up p n times, so this is n times p. Okay. Again, as you see, this is much simpler than this one, but this is also another way of proving combinatorial identities, right? I just proved that this sum is equal to n times p, because I calculated the same thing, the same expected value in two different ways. Once I got this result and once I got this result. Now, of course, you can also prove it with a counting argument. And this is actually just expanding the binomial identity, so it's fine. They're actually the same. Okay. So anyway, these two problems were quite trivial. The point was to just show you that things can become much easier if you use linearity of expectation. Now I'm going to go a bit forward, and I'm going to give you problems where you cannot solve them unless you use linearity of expectation. So the other approach would be just so hard and so painful that I cannot even do it during this whole class. Okay. Let's say for my problem 3 that I want to play a game. And in this game, I have a fair coin. Okay, so it's a coin that gives me heads with probability half and tails also with probability half. Okay. But I keep flipping it until I get heads. Okay. So I flip the coin. If it's heads, I'm happy, I stop. If it's tails, I flip it again. And if it's heads, again, I'm happy and I stop. If it's tails, I keep flipping. Right? So as long as I'm seeing tails, I keep flipping until I see my first heads. And then I stop. Okay. So we have a fair coin. And the question is that we flip it until we get heads. And I'm going to say, suppose X is the number of flips. So how many times am I flipping this coin until I get heads? Okay. The question is, what is the expected value of X? First of all, interestingly, there is a case where I never get heads. So I would have an infinite number of flips, right? If I always just keep getting tails, 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 right? But what is the probability of that? It's just 0. Right? So the probability of getting n tails is 1/2 to the power of n. And if n tends to infinity, that tends to 0. So the probability that you will always get tails is actually 0. So you don't have to consider that. You can just consider the cases where you will eventually get a heads. And the question is, what is the expected number of flips before you get the first heads? Okay. Again, answer me intuitively. It's a fair coin. It's 2. Yeah, 2. Yeah, so I mean, if they ask you how many times on average do you expect to flip a coin until you get heads? 2, right? So we're going to actually prove this. So first of all, it's hard for me to constantly write expected value of X. So I'm just going to show it with mu. So whenever I write mu, I mean the expected value of X. Okay. I want to find a recurrence relation. Now, here's the thing. Suppose that I want to find the expected value of X, then the expected number of flips, which is mu. What do I know about it? So I flip the first coin. With probability half, I'm going to get my heads. And that's it. That's just the end of it, right? So with probability half, I'm going to have only one flip of the coin, right? But with probability half, I'm going to get a tails. And what happens if I get a tails? I'm back to where I was before. Now I have to again keep flipping my coin. And I expect that I would flip it how many times? Mu times, right? So with probability half, I have only one flip. With probability another half, I have 1 plus mu flips. Okay? So solve for mu. I have an equality like this. It's actually a linear equality on mu. And I can solve it, and you can just check this, that mu is 2. So this is a half plus half of 3, which is 3.5. Yeah, that's 2. So 2 satisfies this. Okay, so the expected number of flips is 2. Now, of course, the next thing I want to say is suppose my coin is biased. So problem 3 is going to be, suppose I don't have a fair coin. I now have a biased coin, and I can't count because this is problem 4. Okay. So this is problem 4. I'm going to say we have a biased coin. And this coin gives us heads with probability P. Okay. We flip it until we get heads. Again, I say X is the number of flips, and the question is, what is the expected value of X? So how many times do I expect to flip this coin until I get heads for the first time? Again, intuitively, it's like a process. Every time that I'm flipping the coin, I'm either succeeding, getting my heads, or I'm failing, right? But my probability of success is P. So how often should I do it? On expectation, well, I think it should be 1 over P, right? Again, it's very intuitive, but the way we're going to solve this is exactly like before. So again, I say, suppose that mu is the expected value of X. I write the recurrence. So what is mu? So I first flip the coin, and with probability P, I'm going to get heads. So with probability P, I will have only 1 flip, okay? But then with probability 1 minus P, I'm going to have how many flips? 1 plus mu, right? Because my first flip is going to be tails, and then I expect to have another mu flips in order to get it. Okay, again, linear equation, solve mu, you'll get that mu is 1 over P. Okay, or just again, replace mu with 1 over P, you'll see that we have equality. Okay, great. So these problems were quite easy. Let's now make it a little bit harder. Problem 5. So this is our problem. It says that n people go to a party and each person has a hat. The hats get mixed up in the party in a random way. So each person ends up leaving the party with a randomly chosen hat. Okay. So each person I leaves the party with a hat PI. And I'm showing it with P because this is a permutation, of course. Okay. Now, my question is this. How many people do you expect would have their own hat? what is the expected number of people with their own hats. And I'm assuming here that every permutation is equally likely. Okay. So equivalently, what I'm asking you here is that I've chosen one of the n factorial permutations of the numbers from 1 to n, and I've chosen uniformly at random. So every permutation had the same probability 1 over n factorial of being chosen. And then I'm asking, what is the expected number of fixed points? What is the expected number of indices I such that I is equal to pi? Okay. So I'm saying my random variable x is the number of indices I such that I is equal to pi. And here my p is the randomly chosen, uniformly randomly chosen permutation. And what I'm asking you is what is the expected value of x? Okay. Now, again, I can go to the definition of expected value, right? So I can ask, how many permutations have 0 fixed points? This is exactly the set of derangements, and we know how to count derangements, right? But counting derangements was actually quite hard. I mean, we had a recursive formula for it, but generally we had to use inclusion exclusion, right? And then I can count how many of the permutations have exactly 1 fixed point, how many of the permutations have 2 fixed points, and so on. So this is not good, but it is, again, doable. It's not completely impossible. So the expected value of x is going to be the sum. I'm going to say the number of fixed points is going to be somewhere from 0 to n. Okay, so if I'm going to have I fixed points, so I'm going to say I times the probability that the number of fixed points is equal to I. Okay, but what is this probability? What is the probability that the number of fixed points is I? Okay. Instead of asking what is the probability, let me just ask you how many permutations have exactly I fixed points. Okay, and then I can just divide that by n factorial. That gives me the probability. Okay, how many permutations have exactly I fixed points? If I want to have exactly I people that are in their own location in the permutation, I have to first choose which I people. So that's n choose I. And then these I people will remain in their own position, but everyone else has to be mixed up in a way that no one is in their own position. So n choose I times the number of derangements. I hope I used D before, I don't remember, of n minus I. And we know how to find the number of derangements. We have a recursive formula for that. And of course, since I'm working with a probability, I have to also divide this by n. Okay. So my expected value is going to be this. It's going to be the sum of I from 0 to n of I times n choose I times the number of derangements of n minus I over n factorial. And again, this is ugly. This is hard to compute. Now I want to use linearity of expectation. I want to find a simpler solution. Again, I want to write x as a sum of indicator variables. But this time, I'm going to define my variables like this. I'm going to say xi is 1 if I is a fixed point. So if I is equal to pi in my randomly chosen permutation p. And it's going to be 0 otherwise. Okay. And of course, again, my x is the sum of my xi's. So I can say that because x is the sum of I from 1 to n of the xi's, I also know that the expected value of x is just the sum of I from 1 to n of the expected value of xi. What is the expected value of 1xi? So this is a much simpler problem to answer, right? So when is xi 1? When I is in its own position. How many permutations do I have if I has to be in its own position? N minus 1 factorial, because I have to put I in its own position, and then everything else, I can permute them in whatever way I like, right? So what is the probability that xi is 1? It's just n minus 1 factorial over n factorial, because I have n minus 1 factorial permutations in which this xi is 1, and my total number of permutations was n factorial, and all of my permutations have the same probability. Okay, so what is n minus 1 factorial over n factorial? It's just 1 over n. Okay. But we also said that if we have an indicator variable, then the expected value of the indicator variable is just the probability that it's 1. So all these expected values are 1 over n. So I have sum of I from 1 to n of 1 over n. I have n times n, which is 1. Okay. So the expected value of x is 1. Compare these two. Compare this formula with this. Which one's simpler? It's just 1. Okay. So generally, if I choose a random permutation uniformly at random, the expected number of fixed points is just 1. Okay. So there is another problem that is actually kind of related to this. This was problem 5, right? So this is problem 6. And actually, this is from IMO 1987. The good old days when life was easier. Okay. So this is what they say. They say, let's Pnk, P sub n of k, be the number of permutations, of the set 1 to n. So I have permutations of n items that have exactly k fixed points. And they're saying n is at least 1, so don't consider n equal to 0. Okay. This is what you should prove. Prove that the sum of k from 0 to n of k times Pnk is equal to, I'm not going to even tell you what should I put here? It's equal to n factorial. Okay. So again, Pnk is the number of permutations of the sets 1, 2 to n that have exactly k fixed points, that have exactly k of the items in their own position. Okay. We want to find this sum. Well, there is no probability here, so I can just think of it as a counting problem. I can just say, I want to count something in 2 different ways, and I want to make sure that on the one hand, it's just n factorial, on the other hand, it's this thing. Right? So what does this thing on the left actually count? So it's the sum of the number of fixed points over all permutations, right? Because I'm just saying, take the number of permutations that have k fixed points and multiply that by k. Right? So if I can count this in 2 ways, it's going to give me the answer. It's the sum of the number of fixed points. And in order to get n factorial, you can say, well, if I take any particular I, any element I, there are n minus 1 factorial permutations in which I is a fixed point. So the total sum of the number of fixed points of all the permutations is going to be n minus 1 factorial times n, because I have n different choices for I, and that's n factorial. So we can solve this problem without talking about probability at all, right? But another thing we can do, which is actually what I like more, is that I can just divide both sides by n factorial, right? So this is what I'm going to get if I divide both sides by n factorial. K from 0 to n, k times pnk over n factorial is equal to 1. Okay. What is the left-hand side here? It's the expected value of what exactly? Yes. The left-hand side is the expected value of the number of fixed points. And that's just by definition, right? This is exactly what I wrote here. I mean, I actually computed this thing, pnk, which is this part here, right? But if I just use the same x as before, so if I say that I'm picking some permutation uniformly at random, and if I say that x is the random variable that captures the number of fixed points, okay, then the expected value of x is going to be what? It's going to be the sum of k from 0 to n of k times the probability that x is equal to k. But what is the probability that x is equal to k? The probability that I have exactly k fixed points. Well, it's the number of permutations that have k fixed points divided by n factorial. So it's exactly this, right? So this is equal to my left-hand side here. And it's also equal to 1 because of the previous problem. I've shown that this expected value is 1. Okay. So this is equal to 190. Okay. Great. Let's do another problem. This is problem 7. It's called the coupon collector problem. Do you know what a coupon is? Okay, because your generation never used them. But I mean, I don't know. Do you have electronic coupons or something? Okay. Yeah. Great. We're actually the same generation of this joke. Okay. So coupon collector, the idea is this. You go to a shop every day and they give you a coupon. And there are n types of coupons. So there are n types of coupons. Type 1, type 2 to type n. Every day you go to a shop and get a coupon. So every day you buy a coupon. And when you buy a coupon, you get one of the n types, and you get one of them with the same probability. So every type has the same probability. It's uniform. Okay. You buy a coupon whose type is uniformly random. Okay. Now your goal is to find one coupon of each type. Okay. So you will continue to play until you have one coupon of each of the n types, or at least one, of course. At least one coupon of each type. Now, the question I have is, what is the expected number of days that this process will take? So let's say that x is the random variable of the number of days that you buy coupons. What is the expected value of x? So if n is 1, the expected value is just 1, right? So you go get your coupon on day 1, and you have all types of coupons. What if n is 2? How long do you expect it to take if you want to have all 2 coupons? So on day 1, you're going to get one of the 2 types, right? And then from that point onwards, it's back to this same problem here, right? No, not that one. Which one? This one, right? So on day 1, I'm going to get a coupon. That type of coupon is checked. Now, every day with probability half, I'm going to get the other type of coupon that I'm waiting for. But with probability half, I'm going to be disappointed and have to come back again, right? So I know that after that first day, my expected number of coupons is 2. So my total expected number of coupons is going to be 3. Okay. But a number of days buying coupons is going to be 3. But this is when I have 2 types of coupons. What I'm asking for is a solution for all types of coupons, for n types, every value. Okay. Again, if I want to write the definition of expected value and compute it based on that, it's going to be horrendous. So it's going to be the sum of I. Let's say I is the number of days that it's taking. So I is going to be from 1 to infinity, because maybe I never collect all of the coupons. And then I times the probability that the number of days I have to wait, x, is equal to I. Okay. But how am I going to find this probability? What is the probability that I have to wait exactly I days? So again, we go back to this and look at it combinatorially. So I have day 1, day 2, so on to day I. So in day I, I'm going to get the last type of coupon, right? So whatever, let's call that last type of coupon K, right? And in all the days before day I have to have other types of coupons. So you might think this is easy. Well, I have n ways of choosing the last coupon K, and then I have n-1 coupons remaining. In I-1 days, I have to always pick one of the n-1 types of coupons. So it's just n-1 to the power of I-1, right? But no, the problem here is that you not only have to make sure that in all of these days, you're picking one of the n-1 coupons, you have to also make sure that you cover all the n-1 types of coupons, right? So you have to find the number of onto functions from a set of size I-1 to a set of size n-1 to cover this part, right? So in other words, my probability that x is equal to I is going to be this. I'm going to choose one type of coupon for my last day, for my day I, right? So that's n times. Then I have to choose how to fill up the previous I-1 days. And that's the number of onto functions from a set of size I-1 to a set of size n-1. We've seen how to count the number of onto functions, but it was painful again, right? So we had the recurrence relations and we had inclusion exclusion. That's all you can do here. Okay. And then what should I divide this by? I should divide this by n to the power of I, because every combination is equally likely here. Okay, so I don't like this. Again, I have to somehow divide my x, my random variable x, into several parts. But my random variable x is the number of days. how am I supposed to divide this into a bunch of parts? I can't really divide it into a bunch of indicator variables anymore, right? So I'm going to do something better. I'm going to say this. I'm going to say, let's write down the coupons that I'm getting every day. So let's say on day 1, I got coupon 1, then 2, then 1, then 1, then 2, then 3, then 1, 1, 5, 1, 2, 4. Okay. And this goes on. What I care about is how many days does it take for me to take the first type of coupon? How many days does it take for me to go from one type of coupon to 2 types? How many days does it take to go from 2 types to 3 types and so on? Okay, so I'm going to call this first one x0. So x0 is the random variable, which is the number of days for going from 0 types, which basically means I don't have any coupons, to 1 type. Okay. And of course, x0 is going to always be 1. And then I'm going to have x1, which is going to be the number of days for going from 1 type of coupon to 2 types. In this particular example, x1 is also 1, right? And then I'm going to have x2, which is the number of days to go from 2 types to 3 types. In this case, x2 is actually 4. Okay. Number of days for going from 2 types to 3 types. Okay. And then I'm going to have x3, which is the number of days from the time I had 3 different types of coupons to the time I have 4 different types of coupons, and so on. And generally, I'm going to define xi as the number of days for going from I types of coupons to I plus 1 types. Okay. Now I want to go from 0 types of coupons to a situation where I have all the n types. So I can actually say that my x is the sum of the xi's, where I starts from 0 and goes to n minus 1. Okay. Again, I can use linearity of expectation. So the expected value of x is also the sum of the expected value of the xi's. And I remember that my I went from 0 to n minus 1. What is the expected value of xi? What is expected value of xi? So remember my definition of xi. My definition of xi is that at some point, I have I different types of coupons, and I'm starting counting from that point onwards. And I'm saying, how long would it take until I get the I plus first type of coupon? Okay. I plus first, I plus ones. I don't know how that works. Anyway. Okay. So it's like I've collected some coupons. I'm at a particular day here. I know that before this day, I have I types. And then the question is, from this point onwards, how many days should I buy coupons until I see a new type of coupon? Okay. Now, here's the thing. What is the probability that I just succeed in seeing the new type of coupon immediately in the first day here? Yeah. So look, every one of the n types of coupons have the same probability. I would be unhappy, I would fail if I see one of the I types that I've seen before. So as long as I see any of the other n minus I types, I would be happy. So my probability of success on this day is n minus I over n, right? But what happens if I don't succeed? Well, in the next day, I'm again back in the same boat. I have to try again. And again, my probability of success is n minus I over n, and so on. Does this problem look familiar to you? This is again back to the problem where I had a biased coin and I flipped it until I got heads. So getting heads is my success. Here I was succeeding with probability p every time, and I said that the expected number of flips is 1 over p. Here the difference is that instead of just having one parameter p, my probability of success is n minus I over n. So the expected number of times that I should do this until I get to a new type is just n over n minus I. So what I just proved here is that the expected value of xi is n over n minus I. Great. But then let's just put all of these together. The expected value of x was the sum of the expected values of xi's, which is just the sum of I from 0 to n minus 1 of n over n minus I. Okay, can I simplify this? I can take out the n. So this is the sum of, this is n times the sum of I from 0 to n minus 1 of 1 over n minus I. So what is this? This is n times 1 plus 1 over 2, right? So on. I can just write it this way. I can, well, if you look at this n minus I, it goes from 1 to n, right? So it's the sum of n times I from 1 to n of 1 over I. I'm just changing the parameter there, which is just n times 1 plus 1 over 2 plus 1 over 3, so on, right? And well, if you've passed calculus, you call this the harmonic sum for n. So this is n times h of n. And h of n is this thing. Okay. Great. And h of n is actually very close to the log of n. It's like a constant factor away from log of n. So if you want to think of this as an algorithm, like how long does it take? It takes almost n log n time. Okay. I'm going to give you a problem without the solution because we're running out of time and I was slower than I expected. So problem 8. This is a problem from USA MTS. What is MTS? Mathematical Talent Search. Okay. USA MTS. Okay. This is the problem. It says we play a game and the pot starts at $0. So we have a pot, it starts at 0. Every time we flip a coin, and this is, again, a fair coin. And if it is heads, I'll add $100 to the pot. Okay. If it's tails, I take away everything in the pot. Okay. If it's tails, the pot becomes 0. And you get a strike. Okay. if you get 3 strikes, you lose, and you will not get any money. Okay, 3 strikes is just a loss. Okay, but before every coin flip, you can say you don't want to continue, and you can just take everything in the pot. Before each flip, you can claim the pots. Okay, it's a very simple game. So we're starting with $0. Every time I ask you, should I flip a coin? If you say no, you get whatever money there is in the pot. If you say yes, I flip a coin. If it's heads, I add $100 to the pot. If it's tails, the pot becomes 0, you get a strike. If you get 3 strikes, you cannot play anymore and you don't win anything. Okay? So here's the thing. As you've seen in this course, whenever we play a game, the players are infinitely smart. So you guys are infinitely smart. You're going to play the best possible strategy. Suppose you play the best possible strategy. What is the expected value of your earnings? How much do you expect to earn from this game if you play optimally? Okay. So I'm not going to solve this for you, but I'm going to give you some pointers about how you should define your random variables. So first of all, it really matters how many strikes you have. Okay. So first, imagine the case where you have 2 strikes and try to figure out what's the best strategy in that case. So if you have 2 strikes, it's very risky to say flip the coin because you might get 3 strikes and you will win nothing, right? When would you be willing to take that risk? You would be willing to take that risk only if what you have in the pot is less than the expected value of what you will have in the pot after you take the risk, right? So you have to somehow define these expected values. Okay, and I'm going to give you a hint. In this case, you will only let it go. You will only flip and bet if you have 0 money. If you have more than 0 money, it makes sense to just take it because you have 2 strikes. It doesn't make sense to try another flip, okay? But then when you fix your best strategy for the case where you have 2 strikes, then go back and say, okay, now suppose that I have 1 strike. What is my best strategy now? Because based on your best strategy for 2 strikes, you can compute your expected earnings when you have 2 strikes. And then you can use that to see when it makes sense for you to flip the coin when you have 1 strike. And then so on. And then you do it for 0 strikes. And that will give you the overall optimal strategy. Or you can just ask one of the TAs to solve.